Okay. Should we call him out and unmute him? Jorge, are you there? Hello, Jorge? Nick, he still looks like he's muted on my view. Okay, so he's muted. Okay. Ahmad, are you there? Ahmad? Well, Ahmad's joined us, but we don't see a camera.
Hi, Lane. Do you hear me?
Yes, I can. Is this Jorge?
Yes, see, I am.
Hi, welcome to our Hangout.
Thanks. I'm pleasure to be here.
Well, that's wonderful. Where are you, Jorge?
I'm from Guatemala.
Guatemala. Wonderful.
Yes.
Welcome.
Thanks.
So, do you have a question that you'd like to ask, or a comment, perhaps?
No, I'm gonna ask later. So.
Okay.
When you were deserting other themes, and I'm gonna listen and gonna ask some other questions.
Okay, wonderful. Who's the charming young man with you in your picture?
It's my son.
What's his name?
His name is Jorge Humberto.
Jorge Humberto.
Jorge Humberto.
That's wonderful. Great. Well,
Yeah.
he looks like he's a real joy.
Yes, he is. So I am a pediatrician.
Mm-hmm.
And he says that he wants to be a pediatrician too.
Wonderful. That's great. So how has medical neuroscience been going for you so far?
Well, I'm teaching. I am already teaching neuroscience, and I'm teaching neuroanatomy, and I'm teaching neuroendocrinology.
Yes.
In medicine and psychology academy. So I'm very interested in the course because it's very valuable, all the information, and also the new information because we are know that all the information is changing every time, and all we have in books sometimes is old, perhaps we can say old.
Right.
So that's why I'm here.
Well, that's wonderful. I'm really pleased to have you in the course. And you're right, neuroscience is one of the most fastly changing fields of biomedical science. Thankfully, some aspects of our knowledge are stable. Some of what we understand about human brain anatomy is going to serve us for many decades and even centuries to come. But when it comes to understanding the physiology of the brain and the spinal cord, new information is coming all of the time that can make fairly radical change in how we educate future healthcare providers and future brain scientists, as well as everyone else who wants to know about the brain. So I appreciate your willingness to join me and everyone else in the course and learn together, because it's remarkable how much we learn from one another as we study together in a course like this.
Yes, I understand that, and that's why I took the course. So, and I'm here waiting that we can discuss some terms. So, perhaps.
Okay. So we'll see if other folks want to join us. I don't think we have anyone else joined in the Hangout right now. So if there are some issues that you'd like to discuss, I think you can go ahead, Jorge.
Okay. So there's sometimes we already know that all the communication between the neurons are about the chemical synapses. So when we are talking about the electrical kinds of synapses, the influx is the same, or it changes, or how is happen the communication between these kind of synapses?
Yes, good question. The answer depends upon what kind of circuits of neurons we have in mind. As you may recall, as the brain develops, there are many more electrical synapses and not so many chemical synapses, but as the brain matures and develops chemical synaptic junctions, then the chemical synapses far outnumber the electrical synapses. But electrical synapses persist in certain populations of neurons. One type of neuron for which the electrical synapse is very important are the neurosecretory neurons of the hypothalamus that are secreting stimulating hormones into the portal circulation. It's important for these neurons to be electrotonically coupled because no single neuron can produce really enough neuropeptide to have a physiological effect. So it's very important for all of the neurons to work together as a collective network to release their neuropeptides synchronously. Another example is the inferior olivary nucleus of the medulla. Many of the neurons in the inferior olivary nucleus are electrotonically coupled, and evidently there is a need for those activities to be synchronized as perfectly as possible so that as they stimulate the Purkinje cells of the cerebellum, they may do so with a mass effect, rather than activating one Purkinje neuron at a time. So there are some special populations where electrical synapses serve the purpose of synchronizing neurons that are working together, as opposed to the chemical synapse, which is serving the purpose of conveying a quantum of information that can affect neurons either in isolation or in some kind of an ensemble fashion. And of course, speed is the other issue here. The electrical synapse allows for the near synchronous activation of neurons, whereas chemical synaptic transmission takes time, and sometimes that time element is very critical for physiological function. Others instances, it's not so critical. So we generally think of the chemical synapses as important for conveying information within a network, whereas the electrical synapses are much more important for synchronizing the output of a network rather than conveying packets or quanta of information that are then the substratum over which information processing occurs, or potentially plasticity might occur as well. So those are just some thoughts about that, but one point as a pediatrician to keep in mind, of course, is brain development and the transitions that are taking place, particularly in early life as synapses turn over and electrical synapses gradually give way towards more and more chemical synapses, which of course become the dominant mode of intracellular communication as the brain matures. So thank you very much for your question, Jorge. I think we're still awaiting other guests in the Hangout, so if you have more or further comments, please feel free to fire away.
I went ahead and muted you because you just have to unmute yourself, Jorge.
Jorge, I think you're muted, and if you could unmute yourself on your end, you could go ahead and talk. Jorge, are you there? Yes,
Yeah.
we can. Thank you.
Okay, thanks. I was watching some TED Talks video, and some neurologist says about that some patients with autism diagnosis, sometimes they are misdiagnosed because they could have some convulsive access in some population of neurons that doesn't detect, and they are classified as autism. So it calls me the attention because autism is sometimes called like a diagnosis when you don't have anything more.
Mm-hmm.
So what happened in autism? Is it that every patient or some patient could have convulsions and some others not, or is a matter about the neurotransmission?
Yeah, thank you for the question. Autism is a topic that we did not say much about in medical neuroscience because the underlying biology of this spectrum of disorders is still not so clear. So I think the first point I would make about it is that we are thinking about autism as a spectrum, and individuals may be developing in different spaces within that spectrum, and there may be different neurobiological issues that are afflicting individuals in different locations on this hypothetical spectrum or hypothetical continuum of brain development. I think for some individuals, the problem may be a little closer to the emotional centers of the brain, that is, those structures that are critical for social cognition. And that may or may not include additional brain structures, some of which may have other kinds of congenital issues that could lead themselves toward the development of seizure disorders. So I think it's not one thing, it's going to be multiple issues. What most of these underlying mechanisms seem to affect, though, are those systems of the brain that are important for mediating aspects of social cognition, including how we orient our eyes and our gaze towards another human being, and how our brain in turn interprets the intentions of motor actions that we observe in other human beings, including what we observe around the face and even what we do with the rest of our body. So one of the really fascinating ideas to emerge in recent years is that this so-called mirror motor system in the lateral part of the premotor cortex may be somewhat deficient or perhaps not fully developed in some individuals that are along this spectrum of disorders. And that might impair an ability of one person's brain to encode the intention of the actions of another. And as you can imagine, this could be very important for social communication and social cognition. And if there should be a disorder in such a brain network, it might lead to a lack of understanding of the intentions of the social actions of other people. So something like that may underlie some of what we consider to be autism. But my suspicion is that we will see a broad spectrum of underlying brain biology that relates to this broad spectrum of human behavior, some of which we might consider to be pathological in the sense that it's impairing normal function and normal development, but there will be a continuum that will affect what we consider to be normal behavior as well. So it's a fascinating area of research. I hope to say much more about autism in the coming years in medical neuroscience. We now have a new center at Duke University that is in the works to study autism, led by some leading world-class investigators. So I look forward to learning more from them and from the rest of the community of scientists and clinicians who work with children and adults with this diagnosis.
Okay, thanks.
You're welcome. Thank you, Jorge. Of course, you're welcome to stay with us, but I think we'll see if anyone else wants to join. I saw Melissa jump in here briefly, and
Yeah, she just hopped out. I don't know if she had problems with the internet or not.
okay. So we can just be patient and wait to see if other people want to join. Or I've got Nick with me. He's been with me throughout the course, and he's working the behind-the-scenes aspect of this Hangout. I'm just wondering, Nick, are you getting any comments or any questions from anyone?
There has been no questions on the actual Hangout page. I was actually looking at some of the pre-survey questions on the forum, and I was going to go back to maybe some of the other ones that maybe we didn't catch last week. So,
Sure.
I got a question here. I'm not sure if it's already been answered, but it's what is the future of medical neuroscience, and what are the most heavily researched areas, and what areas of the field still have the most mystery and need for more research?
Sounds like the good day for a TED Talk or something like that. I'm going to ask Nick to mute his microphone so we don't have
get that real quick.
feedback here. Thank you. Well, you know, the future is wide open when it comes to the field of medical neuroscience as brain science discovery begins to impact really everything we do in the medical sciences, in the social sciences, in the behavioral sciences. Some of the areas that I'm particularly excited about, for example, are understanding better the brain mechanisms of plasticity that then can be used to optimize human health, human wellness, and human performance. So there's an urgent need to better understand how the brain can respond to injury and disease so that we can optimize the care and the rehabilitation of those individuals that are afflicted with brain injury and disease. But I think we have tremendous opportunity to understand how to support brain health in individuals that are otherwise progressing through life normally without injury or disease. We have yet to fully understand how to optimize education, for example, for children, for adults, and even for older adults, because as the brain changes across the lifespan, very likely there may be new opportunities to engage the brain in productive ways. So we're just beginning to learn about all of this, but a few of the general principles that I think have emerged so far is that the brain could be considered an extension of the cardiovascular system. So what's good for the heart and for the rest of the vasculature is also going to be good for the brain. So it's not surprising, for example, that one of the best things we can possibly do for the brain is aerobic exercise. Diet and nutrition are also very important to support brain function at every stage of life. And you know, the brain is, of course, the organ that mediates our behavior. And as human beings, one of the most important aspects of human behavior is in the domain of social behavior. So having healthy social relations is important for human flourishing and for brain health as well. So I think we're going to see a deeper understanding of the underlying biology that supports these clinical observations. And I think the future is tremendously optimistic in terms of understanding how to optimize brain function and brain health and brain wellness for all individuals. Now, the other exciting domain that I'll just mention very briefly has to do with technology. I think we're already seeing some just amazing work where technology is beginning to interact directly with brain function in very interesting ways. And it's going both ways. Signals are being extracted from the brain and put to use, and signals are being applied to the brain for therapeutic benefit. So these are just some of the emerging themes that we will see in even my lifetime, however long that should be, but certainly in the lifetime of many of the students in medical neuroscience. So there's much to look forward to in the future. So it looks like Ahmad is back with us. Are you there, Ahmad? You're currently muted, so if you're there, Ahmad, you should unmute yourself and make sure that you can hear us and we can hear you.
Hello, sir. How are you?
I'm very well. It's nice to see you.
Nice to see you again, sir. It's my honor.
Yes, thank you.
I have a question about the anatomy. I've been taking deep consideration about the so as I want some for different neural in the patellar reflex. Is it an axon or is it just a dendrite?
Ahmad, I'm very sorry for much of your question. There was some kind of interruption of the internet stream. Could you briefly restate your question?
Uh, the afferent axon
Yes.
uh, from the patellar reflex. So is it an axon or a dendrite that go to the ganglion?
Yes. Great question. I think I understand what you're wondering. So the information is afferent, that is, it's coming towards the cell body, and normally we would associate that with a dendritic structure, but from a histological perspective, it's very clear that we're talking about an axon that's in a peripheral nerve. So the sensory axons in peripheral nerves that are the peripheral process of dorsal root ganglion cells and cranial nerve ganglion cells, those are called axons because histologically they are axons. However, that they are conveying are traveling into the nervous system towards the cell body, and actually they propagate right past the cell body and into the central process of the very same axonal structure. So from a histological perspective, we call those axons, although from a functional perspective, of course, we recognize that they're conveying afferent information with the letter A, as if they were a dendrite, but we clearly call them axons.
So, sir, a question about the cranial nerve. I see that cranial nerve 9 and 10 are share the common function and origin. So are they just different by the thought? They are different.
Ahmad, I'm afraid we didn't get much of your question, but I heard enough that you're asking about cranial nerves 9 and 10 and their functions and what distinguishes them. Cranial nerve 9 and 10 are very complicated nerves. They have multiple components to them, and some of those components are quite similar, but some are quite distinct. For example, they both convey a sense of taste, a special visceral sense, into the brainstem, but much more is conveyed in taste from cranial nerve 9 than cranial 10. They both have parasympathetic outflow, but much more of the parasympathetic outflow is passing through cranial nerve 10 than cranial nerve 9. In particular, cranial nerve 10, the vagus nerve, as you may know, innervates much of the viscera of the thoracic and abdominal cavities. There are other differences that pertain to the innervation to the branchiomeric muscles that govern the larynx and the pharynx. Some of those details are probably a bit beyond the scope of our course, but we can talk about them if you'd like. So I apologize for not hearing all of your question. Again, there was a little bit of an internet problem when you were speaking your question, so maybe you can try one more time to clarify or add to it.
I just wanted to check if they are nucleus and are the same. How we
Ahmad, I'm so sorry. On our end, we're just not hearing your question. It seems like as you start to speak, something about the internet is failing us, and we're not hearing your question. Perhaps you could maybe use the chat function and type in your question. There is a chat tool in Google Hangout, so perhaps we can receive your question from you that way.
And it looks like Melissa's joined us.
Melissa, are you there?
She's muted as well, so I don't know if she can hear us. She mentioned that she couldn't hear us before.
Okay, so Melissa, if you could unmute yourself on your end, you should be ready to join us live. Well, perhaps Melissa has stepped away. If any of you are out there that have not joined the Hangout, we have space for you, so you're welcome to join. If you'd like to chat out a question, feel free to use the chat function, or you could post something to the query that we sent out a little while ago to receive some questions from you all. Perhaps while we wait to see if Melissa will join us or someone else, I'll ask Nick if he has any other questions.
Yes, there's actually. So this one's from David Lee. Are there any equations better at predicting the reversal potential in neurons than the GHT equation?
Yeah, so I think he's asking about the Goldman equation and the predictions of reversal potentials. You know, I think that that is still the standard in the world of biophysics to predict a reversal potential, knowing that there are always some subtleties that the mathematics is not capturing. But I think that the important concept around the reversal potential is that one simply needs to know the permeant ion and its concentrations inside and outside of the cell in order to predict the reversal potential. And if it's a channel that allows for the permeation of multiple ions, then we have to consider the complexity of the Goldman equation with separate terms for each ion. But as long as we know the concentration gradients, we can predict with really remarkable precision what the reversal potential of that conductance might be. Now, we're talking about a steady state. That's the definition of equilibrium. If one were attempting to model the dynamics of channel activity, well, that would be another matter, and there are more complicated mathematical formulations that we would appeal to if we were to try to really understand in quantitative terms the behavior of an ion channel or the mass effect of many ion channels. So I think the Goldman equation is still an extremely useful way to understand the concept of reversal potential. Melissa, are you there? Well, perhaps not.
I got another question from outside the Hangout. It's from Alexander Yarstev. He first would like to thank you and say this class is wonderful, and this is actually his second run at taking the course. This question is about mental fatigue. He says there's a discussion in psychology about mental fatigue being an emotion or a more deeper resource usage process. I'd like you to comment on that.
Well, thank you, Alexander, and especially appreciate you being willing to join us for a second round of medical neuroscience. That's very encouraging. Yeah, mental fatigue, that's an interesting challenge. I think that our emotions do serve a certain adaptive purpose. They can promote engagement, but they can also have a negative reinforcement value. So I can understand how there may be a perspective that mental fatigue involves an emotional valence that might limit behavior, limit engagement, and perhaps shift us from perhaps a more focused attention to a more default mode of brain activation. So when we think about brain activation, we're now starting to understand about how the brain seems to have networks that operate in certain modes that reflect our engagement with our sensory environment or our memories or our mental activity, which may or may not be related immediately to our sensory environment. So the emotional processing, which we think of as an implicit aspect of brain function, might play a role in shifting the brain from one kind of state to another. For example, it might have some role to play in shifting us from a more focused mode of concentration to that default mode, where we are more internally engaged and less externally driven. So yeah, I think it's a very reasonable way to think about how emotion might influence our thinking, particularly in that context of an extended period of focused concentration that we might think of as mental fatigue. And these are all very testable ideas, and I suspect that there is some literature on this that I'm not familiar with. So I think we can all benefit from maybe checking that out and seeing if we can't inform one another, perhaps on the discussion forum. So thank you, Alexander, for the question. I did get a question about a week and a half ago, which I apologize for not addressing it. I had meant to kick this to the discussion forum, but there was a question that came to me about the issue of timing and whether there was an area in the brain, just as there are areas in the brain that process different sensory signals, might there be an area in the brain that is dedicated to keeping time? And the answer is not entirely clear, but it does seem that the motor system is very much involved with this whole matter of timekeeping. And perhaps that's not a surprise, since one of the things that the motor system does very well is generate rhythmical behaviors. And rhythmical behavior is one way to keep time. So it's really astounding how good we are at keeping time. One can imagine the various ways in which that's important in music, in dance, and other aspects of human performance. So it suggests there is some way for us to keep track of the passage of time and to use that information to predict behavior and to order behavior in sequence. And much of that very likely relies on various circuitry throughout our motor system, including our motor cortex, presumably also including our cerebellum, and possibly even the basal ganglia. If that's what the question was getting at, then I think those would be the places that I might look for an answer. If by the time you had more in view the circadian rhythms of our lives, well, we have another kind of brain circuit that we would appeal to. It would be one associated with the suprachiasmatic nucleus in the hypothalamus and its connections to other hypothalamic nuclei that entrain our daily rhythms. So the whole question of time, I think, is a fascinating one, and the brain has probably multiple mechanisms by which it keeps time and uses such signals to order behavior. Nick, any other questions coming your way?
Yep, I was just looking at one from the pre-survey. There's researchers studying common principles, parallels between the brain and the universe as they assume that the organization of brain and universe are somehow familiar. What approaches and concepts in this area are most potential in your opinion?
Another grand cosmic question. That's great. Well, I think that the methods that we use to study the cosmos and the brain could be one and the same in the following way, that I think that as biologists who study the brain, we have been very slow to adopt quantitative tools and computational approaches. Unlike, for example, the physicists and the mathematicians who have applied those quantitative disciplines to understand the universe at a very grand scale or in a very micro scale, even the microscopic, I'm sorry, not the microscopic, but the nanoscopic atomic level. As biologists, we tend to operate in the mesoscopic scale of organization, and we have been slow to apply, I think, quantitative tools, particularly in the field of neuroscience. But that's beginning to change. So we're beginning to see more collaboration between physicists, mathematicians, computer scientists, and biologists in the study of brain organization, brain structure, brain function. I've had a bit of a taste of this myself, having an opportunity to collaborate with some wonderful physicists who have been developing mathematical models for understanding the development, the evolution, and the organization of cortical circuitry. And you may have heard me talk some about this in our lessons on the visual cortex, where I related a bit of a discovery that we made a couple of years ago, looking at the organization of circuits in the visual cortex, where we found what we thought was really a remarkable degree of quantitative precision, and even a mathematical constant that characterized the distribution of circuit elements. And that constant, as it turned out in our model, was pi. In our observation, it was 3.14 with some margin of error surrounding that value. So I think that's an example where quantitative tools can lead to new insight into the organization of the brain and can be used to build models that have predictive value that helps us to do better experiments, to try to have a deeper understanding of the brain. So I think in some sense we've borrowed the tools from cosmology and have applied them to the brain. I do think there are interesting parallels in complexity and order that one could recognize. But I would note that our Society for Neuroscience has recently changed one of its statements of complexity. You've heard me declare numerous times now that the brain is the most complex organ of the body, and we've recently revised that statement in our society to claim really a bold assertion that the brain is the most complex structure in the universe. So we've yet to fully test that assertion with our colleagues in cosmology and physics and mathematics, but it would be an interesting discussion to have.
And I have another question from the previous Hangout that didn't get answered. And then this was from Maria. She asked a question in the forum about the correlation some studies have found between, excuse me if I'm pronouncing this wrong, anosmia and Parkinson's disease, but apparently nobody was able to give a clear answer. So she would like to know whether there's plausible physiological explanation considering the physiology of the olfaction and how far the olfaction apparatus is located from the substantia nigra.
Great job. Thank you, Nick. So Nick is not coming to us in medical neuroscience with a background in the field of neuroscience, but he's made tremendous progress on learning the field of neuroscience and neuroanatomy. So the question is about anosmia and Alzheimer's disease. Anosmia means a lack of the sense of smell or a lack of the olfactory sense. This has been long recognized as one of the features of Alzheimer's disease. Not necessarily anosmia, which quite literally means the absence of smell, but perhaps a blunting of the sense of smell or an alteration of the sense of smell. And sometimes this can be tested clinically by simply having some kind of odorant that a clinician might be able to pull out of a bag, such as a bag of coffee grounds, and ask if patients can identify that particular scent. Most of us have probably enough experience with coffee grounds to be able to identify that if we had an intact olfactory system. So what we've discovered about Alzheimer's disease, and this has been known for at least 20 or 30 years, is that some of the central olfactory structures are among the earliest of structures to develop the hallmark feature of Alzheimer's disease at the microscopic level. And I'm referring to the presence of neurofibrillary tangles within neurons and the presence of amyloid plaques. So these plaques and tangles are found in many of the structures that are receiving input from the olfactory bulb. There's an anterior structure just where the lateral olfactory tract begins to meet the posterior frontal lobe called the anterior olfactory nucleus. That structure is affected very early on. There's a broad cortical distribution of plaques and tangles that afflict the piriform cortex, the entorhinal cortex, and an extent of the parahippocampal gyrus. So the hippocampus probably has received more attention over the years as being a structure that's impacted early in Alzheimer's disease. But clinicians have long known that some of these central olfactory structures are also affected. So loss of a sense of smell very well is to be expected in individuals that are developing Alzheimer's disease. And I think there are consequences for that for caregivers and for clinicians. So one might anticipate with a change in the sense of smell, there may also be a change in one's enjoyment of food, or at least one's expectations for the taste of food. So one should be mindful to support the nutritional status of individuals that are beginning to experience changes in their olfactory sense with the development of mild cognitive impairment and its possible progression to Alzheimer's disease.
We have another question. Can't read the name, but it's could you tell us a little bit about structural correlates of impairments of executive functions in ADHD, ADD patients?
Yeah, structural correlates have been very difficult to pin down with attention deficit hyperactivity disorder and the various other kinds of attention-related dysfunctions. So There have been reports of changes in the basal ganglia, in the cortex, in the cerebellum, but to my reading of the literature, there has not been consistent observation of structural change that we believe underlies any of these conditions. That's not to say that it doesn't exist. It's just that there has not yet been clear consensus as to the nature of those changes. It may be that there are no such compelling structural changes, that the change is more at the functional level, at the level of the neurotransmitter systems that can modulate behavior. We know that drugs that affect the dopamine system, for example, are among those that are most effective in controlling the less desirable consequences of attention deficit hyperactivity disorder. So I think with that said, one might imagine that there may be some changes at the level of individual synapses. But as far as gross structural changes and morphological changes in the brain, there just does not seem to be a strong consensus as to what that might be. So this is an area of active investigation, and I suspect we will begin to develop more of a structural phenotype to accompany the behavioral phenotype that receives that diagnosis.
All right, that's the one from one of the pre-surveys. In the case of metatropics receptors in the retina, why is presence of light have to decrease the amount of glutamine?
Okay, I think what the question is getting at is the receptor that transduces a photon of light into a change in the electrical functioning of the photoreceptor is a protein that is the same structural class of protein as what we find at postsynaptic membranes in metabotropic receptors. So what we're talking about is a 7-transmembrane protein that's associated with a set of G proteins in the outer segments of these photoreceptor cells. So the transduction cascade involves a twist in the structure of 11-cis retinal, and that leads to a morphological change in the structure of the opsin protein, which is that 7-transmembrane domain structure in the membrane. And so that conformational change will activate the G protein that we call transducin, and that leads to a cascade of events that ultimately break down cyclic GMP. And cyclic GMP is the second messenger system, the nucleotide, that is essential for maintaining a cation selective channel in the open state in the plasma membrane of the photoreceptor. So when light strikes a 11-cis retinal molecule and induces this series of reactions, some tens of milliseconds later, there is a significant change in the membrane potential as these channels close and the photoreceptors hyperpolarize. So that's the key physiological fact of phototransduction to keep in mind, that the interaction of a photon of light with the photoreceptor leads to the hyperpolarization of the photoreceptor. So as the photoreceptor is hyperpolarized, that means that it is going to have less release of neurotransmitter, and that neurotransmitter is glutamate in all likelihood. And so when a cell is responding to light, it will release less glutamate than it would in the dark. So it's maybe a little bit counterintuitive, but the important point is that there is a change in the release of neurotransmitter that represents the transduction event of light striking the photosensitive pigment.
And it looks like Melissa has tried to join us again.
Are you there, Melissa? I'm sorry if you're having some technical challenges on your end, but I hope you get to sort those out. We'd love to have you join us and ask a question.
So I have another question from last Hangouts forum. This is from Callie Strickler. The question has to do with a neuropathic systemic disease reflex sympathetic dystrophy, complex regional pain syndrome. Have there been any brain scans done on affected patients to show the difference in regard to brain activity on a normal pain day versus a day when the patient is in flare, whether there are different parts of the brain that are more or less active and responsive during a flare.
Well, thank you. I think Callie was the name. Thank you, Callie, for the question. I don't know off the top of my head of any studies specifically on the regional pain syndrome that you have in mind. I do know, generally speaking, though, that studies of pain, be it acute pain or chronic pain, do reveal different patterns of brain activation, different magnitude of brain activation in certain key parts of the brain that seem to be important for the experience of pain. And I think at this point it's probably important to try to differentiate the notion of pain in terms of nociception, which is the ability to detect the presence of pain and to localize that with somatotopic precision, and the affective dimensions of pain, what we sometimes refer to as suffering. So some of the brain structures involved there, so as you probably know or can readily imagine if you've been with us this long in the course, that the postcentral gyrus is very important for nociception. It allows the localization of a painful stimulus with somatotopic precision and rather rapid processing time as well. On the other hand, this issue of the emotional content of the pain, that aspect of the pain that we might interpret at times as suffering, that is a slower process, but it's also a more persistent process, and it's one that engages emotional centers in the brain. And one important aspect of that emotional brain network that seems to weight its activation with our sense of emotional burden with pain is the anterior part of the cingulate gyrus. So this is a part of the brain that seems to detect the presence of an unexpected signal that has a profound impact on our state of body and brain. And so suffering, the emotional burden of pain, is one such stimulus. So the more intense is the activation of the anterior cingulate gyrus, the more likely is a person in pain likely to be experiencing suffering. So my guess would be for these kinds of studies of regional pain syndromes associated with the autonomic nervous system and this idea of autonomic dysregulation as being one of the triggers of such pain, that we would likely see different activation patterns in the anterior cingulate gyrus as a function of the subjective experience of the pain itself. Some interesting studies have been done on this using things like hypnotic suggestion, meditation, other means by which one might try to intervene in the experience of pain. And sure enough, if it's possible to lower the subjective experience of pain, there very likely is a commensurate reduction in the activity of this anterior cingulate region. And it leads one to hypothesize that the level of activity in the anterior cingulate is what actually is evoking this sense of the suffering that accompanies the experience of pain. So this is a huge problem, and it's one that I think we can explore novel means by which we can engage this anterior cingulate gyrus and try to modulate or manipulate its activity in a therapeutically beneficial manner.
David Lee asked a question, what do you think of the Human Brain Project in Europe?
Europe has invested heavily in the Human Brain Project, as has the United States, but I think the European investment is much more significant than what the United States government has invested. As a brain scientist, I have to be enthusiastic about seeing greater resource being brought to discovery about the brain, although I understand that even with a huge initiative like the Brain Project, that there is still money that is being diverted from other urgent needs. And so I think we really need an interdisciplinary perspective to have a sense on whether this is money well spent or not. There are different aspects of the BRAIN initiative. I'm more familiar with those aspects in the United States than I am in Europe. But I think those projects that are really aimed at developing novel methods for understanding the brain are very much worthwhile. Those methods that are aimed at generating a more complete description of brain connectivity and brain function, I must admit I'm a little bit skeptical about that particular approach. I have many wonderful colleagues that are deeply involved in this process, and I certainly don't mean to be skeptical of anyone's particular research program. But I do wonder whether that money is best spent at these strategically targeted initiatives rather than promoting a more basic fundamental level of discovery where the consequences of that discovery are not so predictable, but perhaps will be hugely beneficial in the long run. This has been the history of science, particularly biomedical science, and I expect that that might continue. So I am just slightly suspicious of major governmental initiatives that would try to shape the direction of science. Certainly we have wonderful examples where that has been just tremendously fruitful and profitable. I'm thinking, for example, of some of our space exploration initiatives over the years. But when it comes to brain science, I think our money is best spent at a basic fundamental level, and we'll see where that may lead us. So the BRAIN Initiative, I think, is a wonderful project. It has been in the works for a long time and has already generated some marvelous insights into the organization and the structure, the function of the brain. I think we just have to be very cautious that we are proceeding in an interdisciplinary fashion so that we can best benefit from the discoveries that are being made.
Okay, this one is from Paula. Just came in. Can you explain how one knows from, I believe it's from case 1 from the final exam preparation, that the lesions in the thoracic spinal cord versus the lumbar or sacral? I'm not sure if these are spelled right. Thanks, and thanks so much for the excellent work you do and for sharing so enthusiastically with us.
Okay, well, thank you very much for the question, and I am going to jump onto the website, which I am not there currently, and just make sure I have clearly in my mind the case that's being mentioned. So this is a case from, I believe it's the practice set that I've made available for preparing for the final exam.
Yes, case 1 from final exam preparation.
Okay. So I will jump over there. And if you're out there tracking along, I would encourage you to do so as well. So you can just get onto our website and go to quizzes and exams. And final exam preparation. And just go ahead and jump on this quiz. This is really just for practice. So this is an individual who had a history of hypertension, cigarette smoking. So these should make you think that he perhaps is at some risk of cardiovascular disease. And he is undergoing an abdominal angiogram to evaluate an aortic aneurysm. Well, in the process of performing this procedure, something really bad happens. So this individual within the hour develops paralysis in both of his legs with urinary and fecal incontinence. And later that day, an examination reveals intact sensory and motor functions in the cranial nerves. With respect to motor function in the postcranial body, there was flaccid paralysis of the lower limbs with an absent knee and ankle reflex. And there was no response to plantar stimulation of either foot. The bladder was greatly distended, and with respect to the somatic sensory systems, there was diminished response to pain and temperature stimuli over the legs with some perianal sparing, but the vibration and position sense, and I might add other aspects of mechanosensation, were normal in the legs. So this suggests that there is a problem on the ventral aspect of the spinal cord, and the question that I believe it was David was getting at is it a problem in the thoracic cord, in the lumbar cord, or the sacral cord? Now, if this is all you knew, just in the acute presentation phase, it wouldn't be so clear where the injury was, because you might be wondering, is this a case of a lower motor neuron injury or an upper motor neuron injury? It certainly looks like a lower motor neuron injury on the day of presentation. And this is where time is important. So if we read on in the case, we see that over time, over about a week, things begin to change. What was initially a flaccid paralysis of the legs has converted to spasticity. So this is a fairly typical presentation of the phenomenon of spinal shock following an upper motor neuron injury. So now we understand that the weakness in the legs that initially were flaccid and paralyzed, now spastic, must not be due to damage to the lumbosacral enlargement of the spinal cord. Otherwise, it would be a persistent lower motor neuron injury, and we would not expect to see spasticity, which is a sign of upper motor neuron impairment rather than lower motor neuron damage. So the best way to understand this patient is to imagine that there was some event that affected the way our upper motor neuronal systems are conveying signals into the lumbosacral enlargement with sparing of the lumbosacral enlargement. Now, we know that the upper extremities, well, actually, we don't make a specific comment about that, but since they're not pointed out as being impaired, you can assume that those functions are within normal limits. So the problem must be below the cervical spinal cord. And the obvious place to think about this would be in the thoracic cord. Now, with respect to what actually happened to this gentleman, very likely what happened was that during the process of doing the abdominal angiogram, there might have been an embolus that was dislodged and passed out of the aortic trunk and into one of the arteries that supplies the spinal cord. And there's a particular artery there called the great radicular artery of Adamkowitz that is often the culprit in this situation. Eventually, very likely, an embolic stroke of the anterior spinal artery is what happened in this gentleman. And that embolic stroke of the anterior spinal artery, being a single artery along the midline of the spinal cord, explains why is there bilateral damage to this case. And if you look at the blood supply to the spinal cord back from Unit 1, you'll see that the sulcal branches of the anterior spinal artery supply the ventral horns and extend into the lateral columns of white matter. And so the upper motor neuron damage in this case involves compromise to the lateral cortical spinal tracts, passing through the lateral columns of white matter in the spinal cord. Now, there is a lower motor neuron injury in this case. It's just that it's very likely the thoracic cord. And since the thoracic motor neurons are innervating axial muscles, it's less clinically obvious how those might present. And they're often not tested, actually, in clinical assessment. So I hope that's helpful. Just keep in mind that in order for the legs to be spastic, the lumbosacral enlargement must be functional. So that's the key differentiator between the thoracic localization of injury and something more inferior to that level. So thank you for the question there. I hope that you are working your way through this practice quiz to help get you ready for our final exam. It certainly is designed to be of benefit to you as you prepare for the final, and you can expect questions of this basic paradigm as you get to the final if you've not gotten there already.
So there's another question that came in. A question's about auditory processing of tone, pitch, and language. Is there a lateralization difference of lexical tone and non-lexical tone?
Yeah, that's a wonderful question. I am struggling to think about whether I have an answer for you on that. My guess is that that has been studied. I think I would have to consult some of my colleagues here at Duke that work in the field of neurolinguistics to get a better answer for you. My guess is that there may be some interesting differences there. Those differences may relate not just to asymmetries of function on one side or the other, but perhaps even the magnitude of asymmetry that one observes, as is the case for the phenomenon of perfect pitch, for example, perhaps a related phenomenon. So I'm sorry, I don't really have a clear answer for you on that one, but I'll see if I can find something out from my colleagues here at Duke.
I'll throw this one up until I find another one. Can you give your views on consumer neuroscience?
I'm not sure exactly what you mean by consumer neuroscience. Perhaps what you're referring to is what we like to talk about here at Duke as decision science or decision neuroscience, which is the science of how it is that we make decisions. And one domain of life where we make decisions all the time that seem to be very meaningful to us are decisions regarding our finances and decisions regarding how we spend money on items. There's also a marketing component to this that you might have in mind. That is, how do the advertisers and the marketers design their products to appeal to us that might inspire our consumer decisions. So I think there's a rich brain science here. It's just getting started, and I think we will learn much more in the future about how our brains are integrating information regarding the decisions that we have to make. And there's something about finances that just is deeply personal to us and seems to engage our brains at a level of decision making that many of the other decisions we make in life just don't seem to have the same demand. So we have, in fact, at Duke University now, a certificate program that's available to our students to receive special certification in this domain of decision science. And the brain science of decision making is a big part of that. So there is actually another Coursera course out there if you're interested in this topic related to decision neuroscience. And I hope some of you might pursue that as well as more generally contribute to this emerging field. I should just say, because some of you may be in the world of behavioral economics, that behavioral economics has been very productive and interested in this question for many decades now. So neuroscientists are sort of the latecomers to this field, but I think what neuroscience can bring is a biological framework for understanding human decision making. And this will be germane to many aspects of life, and I look forward to seeing further discovery in this field in the future.
All right, so one of these questions came from one of the previous pre-surveys. The role of stem cells in brain plasticity and its implications on the future of treatment methodologies after certain incidents such as stroke or head trauma.
Yeah, so I think stem cell therapy for brain repair is one of those areas in the field of medical neuroscience that we should all be watching for in the future. I think there was initially quite a bit of excitement about this possibility. My read on the field is that maybe the excitement is dampened down just a bit. There are a couple of perspectives here. One is, well, what about the brain's own intrinsic stem cells? Might there be an opportunity for the brain to use those stem cells to repair itself? And then the other idea is, well, can we promote the recovery of brain tissue by providing exogenous stem cells, be they cord blood cell derived stem cell populations or stem cells that are harvested from embryonic tissues. The risk there, of course, is that there are a variety of ethical considerations and lots of people on different sides of these perspectives about whether certain aspects of this research are things that we ought to be pursuing. But for those avenues of research that we seem to have consensus that we should be pursuing, there are questions about how can we regulate the differentiation and the final fate of those stem cells that we might hope would repair the brain. And there's considerable risk, of course, because we don't yet understand all the mechanisms that regulate differentiation and fate determination in pluripotent cells. One possibility is that these cells might respond to some extrinsic signals as well as the intrinsic signals that the brain itself is producing. And I think what we've learned from some early studies is that there is great potential, I think, for such exogenous stem cells to be integrated within a circuit. Unfortunately, there's also some potential for alternate fates to develop, including tumorigenesis. So that would be a major concern, that we wouldn't want stem cell therapy to lead to the development of tumor, with the goal being obviously something far different from that. With respect to the endogenous stem cells, there has been some evidence to suggest that stem cells might migrate to a site of injury, and the hope would be that then those cells might contribute to the repair of the tissue. It's not so clear that that's happening, actually. The stem cells seem to be associated with the vasculature. They may contribute to angiogenesis around a region of injury rather than the repair of the neural structures themselves. But these are all wonderful ideas that need to be more fully investigated through the appropriate preclinical research studies. I think this is one domain of medical neuroscience where we need to really proceed slowly into clinical trials and really make sure that we do our work on the preclinical side adequately, so that we can be sure to mitigate the risk that any patients might experience as they engage in the early phases of clinical trials around these ideas. So thank you for that question. Looks like we have Toddy here. Toddy, am I pronouncing that correctly? Are you there? Looks like Toddy is muted. Oh, there you are. Are you with us? Toddy, I'm sorry, I can't hear you. Can you hear me? Okay. I'm sorry, I can't hear you. It looks like you're muted on my end. Could you try unmuting yourself again? Oh, I'm sorry, I can't hear you.
Toddy, if you can use the chat feature, I should be able to see your question if you have a question. It's a little blue button on the top left side of the screen. Are you able to see her question?
Well, I see that Toddy has written that she's sorry. I think she's typing something, and we'll be patient and see if it gets into something shortly.
She's been trying to get in for quite a while now.
Okay, Fmri Techniques, we got that much of the question. So Toddy's question is about Fmri techniques, and it's what are its limitations to educational practice at school? Well, there certainly are limitations to Fmri as a technology. It provides a very broad picture of brain activation. It's a very indirect way to try to get at brain function. And with respect to educational practice, I'm not exactly sure what you're getting at, Toddy. It makes me think that maybe you're wondering about can we use Fmri as a way to understand different learning styles or different ways to tailor education to most effectively engage different individuals whose brain function might be somewhat diverse. If that's what you're thinking about, it would be a very expensive way to try to get at these kinds of questions, but potentially an interesting research project to try to assess. One might imagine that there are some individuals whose patterns of brain activation are different from others, and that certain educational methods might more directly engage a person's brain than others. So from that standpoint, perhaps Fmri might eventually be used as a screening tool to try to understand what kind of educational activities might most resonate with a learner of a particular style. Now, you know, again, I think there's potential there. It's a little bit difficult to imagine how one would put that into practice, particularly given the cost of this technology and its limitations. So, you know, one of the things that I'm concerned about is that fMRI is a way of assessing the brain when we can clearly differentiate one brain state from another. And that's not always so easy to do. So one person's brain state might be quite similar to another, but be just below detection threshold, which might lead to a very different picture with the fMRI methodology. So I sometimes liken it to trying to appreciate an iceberg when we can really only see a small portion of that from above the surface. When it comes to techniques for measuring the working, living human brain, we are above the surface trying to gain a deeper appreciation for things that we know we can't see directly. And so this iceberg metaphor is one way that I've tried to grapple with the nature of this problem. And sometimes I think the icebergs are visible, and we get a sense of where they are and what their magnitude is. Sometimes that iceberg may slip just a little bit below the surface, and we might miss it entirely. So I suppose I would be concerned with this general approach because of the potential for false positives as well as false negatives. Okay, so if our underlying motivation is to really explore what we sometimes talk about these days as neurodiversity, then I think that's a terrific motivation to try to use fMRI and less expensive alternatives such as electroencephalography to try to characterize what makes our brains different and potentially most teachable in different ways in different contexts. So understanding neurodiversity, I think, is a huge challenge in education as well as in brain science research. So I'm sorry that we weren't able to hear your voice, Toddy, and know really what your question was getting at more specifically, but feel free to chat some more, and we'll be monitoring the chat, and perhaps we can pick up some more questions from you. If you could just indicate in your chat where you are, that would be interesting. Where are you in the world, Toddy? Ah, you're in Brazil. Thank you for letting us know. You know, Brazil, I believe, is the #3 country on our list of participants in medical neuroscience. So I've never been to Brazil, but it's making me want to go because I know there's some wonderful things happening in Brazil in terms of medical education and science and research. Of course, at Duke, we have many connections to the neuroscience community in Brazil. You may know about one of our wonderful colleagues here, Miguel Nicolelis, who is involved with the Walk Again project that was showcased at the World Cup last summer. We're all very, very excited about that work. And what our colleague Miguel has been able to do, and the new Neuroscience Center in Natal, that he's been very instrumental in helping to coordinate. So thank you for your participation, Toddy, and I wish you all the best in your studies of medical neuroscience.
Brazil is actually #2.
#2, there you go. So the United States continues to occupy the top position with about 29–30%. And what's Brazil? About
6%, 6 or 7%.
6%. So that's wonderful. We have about 170 nations now represented in medical neuroscience. So Brazil is #2 of the 170.
This question just came in. Can you please share your views upon using focused therapeutic ultrasound as non-invasive procedures for clearing beta amyloid plaques via microglia and memory restoration?
Yes, well, this is one of those technological advances that I alluded to earlier in this Hangout about the future of neuroscience and things to watch for. So focused ultrasound is a way to provide a non-invasive signal that can penetrate through the tissues of the head and impact the brain. So it's non-invasive in the sense that we're not actually opening up the cranium. It's not brain surgery, but it's invasive in the sense that we're focusing energy that can interact with the brain tissue. So one idea is to use this technology as a way of trying to create focal ablations of pathological structures within the brain. So I think there's great potential for this technology to be used. I don't understand the limitations of the technology currently. I'm not sure how well focused the energy can be, so it's not clear to me really how focal might this application of the technology become. It's also not clear how deep this energy can penetrate. So one might imagine that this could be very useful for more superficial regions of the brain that might be accessed with the technology. I just don't know the limits and how deep into the cranium, to the interior of the brain, this technology might be applied. But there was a colleague who was involved with medical neuroscience in the second run that has been very instrumental in the development of these approaches. So one might look for his work. There was a TED Talk on this technology, and I would refer anybody interested in this to that particular TED Talk.
One question that came in through the chat: do you believe in the theory of gliotransmission?
Gliotransmission? I think what this question might be alluding to is the idea that the glia can participate in the communication of signals within the nervous system. There is now, I think, very clear evidence that glial cells can participate in the transmission of signals, even chemical transmission of signals. What's not so clear is what is the functional role of these signals. That is, how do these signals shape the processing of information in neural circuits? So I think there's much to be learned about this. We do know that some of the signals derived from glia can interact with neural structures and influence their long-term structure and function. So for example, there are signals derived from glial cells that can influence the formation of new synapses and presumably also the dissolution of synaptic structures. But what's not so clear to me anyway is whether there are glial-derived signals that can directly modulate the information processing functions of neural networks. I won't be surprised if it turns out that we gather more clear data indicating that that's exactly what's happening. So, you know, the word glia is a short derivative of the proper term neuroglia, which was coined more than a century ago, capturing the idea that the glia represent the glue, which is what glia means, the glue that holds the nervous system together. So neuroglia would be nerve glue. And that has led to at least a century of rather passive thinking about the role of glial cells in the brain as performing supportive, nutritive functions. But I think what we now understand is that they're much more intimate partners with neurons in the work of the brain. What I don't yet have a strong sense of is whether they function at the millisecond time scale, as would those elements of neurons that are generating, propagating, and transmitting electrical signals. Those signals derived from glia tend to be operating on a much slower time scale, on the order of hundreds of milliseconds to seconds. That still may be very important, but it's not fast enough to have an immediate impact on information processing in the brain. So we'll see how this shakes out. There are a lot of people doing tremendous work on glial cells and glial signaling, and I'm sure we're going to learn much, much more in even just the next few years.
We only got about 10 more minutes. Shu Hong just joined the chat.
Okay, Shu Han, if you would like to unmute yourself, feel free to join us and tell us what's on your mind.
Thank you, sir. I want to tell you that due to my professional exam in MBBS course in Bangladesh, I am not able to attend these course exams. So is it possible for me to attend the next session of medical neuroscience and do the full course again? Is there any possibility?
Yes, absolutely. We don't have yet a plan in place for exactly when the next session of medical neuroscience will run. We know that we at least want it to begin in January of 2016, but we may be offering medical neuroscience again within calendar year 2015. We just haven't sorted that out yet. You are more than welcome to join us again, and hopefully being with us up to this point, you might be able to skip many of the videos and just go right to the quizzes and progress on to where you may have had to step out this time through. So, and the same goes for any of you out there. You're more than welcome to join us in the future for future editions of the course. Many of you know that we're about to launch a shorter version of this course that we're calling Foundational Neuroscience. That class begins in just about 10 days, so you could join us at that point if you'd like. Now, that course is designed to be more concise and to focus more on the neural mechanisms of sensory perception and motor control for the generation of action. So there's not content there about brain development and not nearly so much about higher brain function. And frankly, not quite as much about anatomy either. But if you find it useful to progress through that course and actually complete it and possibly earn a certificate, then you'd be very welcome to do so. So that starts on March 30th. So you're welcome to join us as soon as March 30th. Otherwise, be looking for an announcement probably in a few months about when we will be ready to repeat medical neuroscience.
Thank you, sir, and that was very informative, and I will try to join your the next. What was the course name, please?
It's called Foundational Neuroscience.
Okay, I will try to join it now, in fact.
Okay.
Thank you, sir.
You're welcome.
Okay,
I look forward to seeing you then, Shohun. Thank you.
Okay, sir.
So just maybe a couple more questions. This one's from Deborah. She just she wanted to clarify when the words ganglion, nuclei, nerve tract, and pathway are used.
Sure. Sometimes the terms that we use to describe the anatomy of the brain can be confusing and sometimes even contradictory. Let me try to break some of those down. The word ganglion refers to a collection of nerve cells, and the proper use of the word ganglion refers to a collection of nerve cells outside of the central nervous system. The best example would be a dorsal root ganglion, for example, and the ganglia associated with the cranial nerves. The problem is that we also use that term ganglia or ganglion to describe this central cluster of brain cells at the base of the forebrain. I'm speaking, of course, of the basal ganglia. It's the only usage of the word ganglia that doesn't refer to this external collection of brain cells. So unfortunately, we have a bit of a contradiction with those terms. Now, the word nerve is another one that is mentioned in the question, which I find this one to be a bit curious. I think from a histological standpoint, we should reserve the use of the word nerve to the structure of the peripheral nervous system that connects the central nervous system to the targets out in the peripheral tissues of the body. So we have the spinal nerves and we have the cranial nerves. That's the best usage of the word nerve. Sometimes that word nerve is used to describe pathways within the brain or the spinal cord, and sometimes the term nerve cell is used to refer to a neuron regardless of where it is in the central nervous system. I think we would all be best served if we only use the word nerve to describe the peripheral component of the peripheral nervous system, and use terms like neuron and tract and pathway to describe the central processes of neurons and their axons. So regarding those pathways, so a pathway usually refers not just to one bundle of axons, but really in an extended set of neurons that are connected in series. So for a bundle of axons, we call those tracts. We might use the Latin word fasciculus or funiculus, but most of us in common English would call them tracts. Sometimes we call them projections. And what they really are, however, are bundles of axons that are compacted together into a small region of white matter. So I hope that helped. I just touched on a few of those terms. There are many other terms that we could have described and tried to explain, but I think I'll pass on those and see if maybe Nick has one final question for us.
Actually, yeah, so this one is from Susan. In your tutorials, you mentioned that autistic spectrum disorders have too many synapses and hence a thicker than normal cortex, whereas ADHD has delayed synaptogenesis, resulting in a thinner than normal cortical layer. The question is this thickness of cortical layer evident in MRI or CT or PET or EEG or other non-invasive test?
Yeah, so the evidence that Susan is referring to comes from a set of studies that were done, I guess, almost a decade ago now, and there have been others since then, that are based on MRI evaluations of the human brain. And these are data that come from studies where the volume of gray matter is assessed. And in some of these studies, there has been opportunity to assess individuals longitudinally, so the changes in their brain over time can be studied. And the suggestion is that there may be changes in the thickness of the cerebral cortex as measured with, for example, T1-weighted MRI imaging. Now, these changes in gray matter thickness are likely representing changes in the numbers and the density of synaptic connections, rather than, let's say, the overall numbers of neurons. Although we can't really differentiate those possibilities in an MRI, I think most of us would assume that what makes the cortex more or less thick and different individuals very likely relates to the volume of tissue that's occupied by the connections, rather than the cell bodies themselves. So there's some evidence to suggest that in autism spectrum disorder, there may be actually an overproduction of these connections, or perhaps a possible defect in the way those connections are pruned down as the brain comes out of childhood into adolescence. So, as I alluded to earlier in this Hangout, it's been really tough to find consensus around these kinds of morphological evidences that we might say underlie autism spectrum disorder, or, on the other hand, attention deficit hyperactivity disorder. So these are some of the more consistent observations that have been made, but even those, I think, need to be borne out with further study in different populations of individuals to try to really understand what's going on here and how consistent are these effects, and whether there are focal effects. That's another big issue here, whether these changes are mainly affecting one part of the cerebral mantle or another. It does seem as though the prefrontal cortex is one area that is subject to a different trajectory of development along the autism spectrum disorder. But I think we need to reserve our final consideration of that until we have more definitive data available to analyze. So I think at this point we probably need to wrap this up. I chose a different setting for this particular Hangout. I'm not sure that you can see what's behind me, but I wanted you all to have a better look of our campus. And it's actually a cloudy, rainy day, but off in the distance there is the cathedral at the center of our campus called the Duke Chapel. And here's a little bit of the beautiful pine trees that we have scattered about our campus. And then right behind me here is the Bryan Research Building, which is the home of the Department of Neurobiology at Duke University, as well as the Center for Alzheimer's Disease Research at Duke. So with that, I think Nick and I will be signing off for now. And thank you for joining us. Thank you all for hanging with us nearly to the very end of medical neuroscience. So as you prepare for the final exam and work through the final lessons, I wish you all the best. Keep questions coming to our discussion forum, and myself and our wonderful community teaching assistants will continue to do what we can to support you to the very end. So Nick, is there any last word from you before we sign off here?
No, I think I'm good. Everything's ready to go. Just appreciate everybody from coming in, and good luck on the final exams, and hopefully we'll see everybody in foundational neuro and hopefully another generation of medical neuroscience, whatever that may be.
Okay, well, thank you everybody for joining us, and we'll see you next time.
Thank you, Lynn.
You're welcome.